Hello, welcome to the tutorial on antenna simulation. So today we're gonna simulate a half wavelength dipole antenna and advance this to the Yagi-Uda microwave antenna. So since this is microwave project, we use HFSS solver in ANSYS. Right, so I right click the project and insert HFSS design as a first step and give a name to this project, something like Yagi-Uda antenna, because the final goal is to simulate Yagi-Uda antenna. All right, and save it. So our dimensions are in millimeters. I don't need to change the dimensions. The frequency of my operation, the operation of my antenna, will be something around 2.5 gigahertz, which corresponds to, according to online calculator, it corresponds to the length of 12 centimeters. Okay, so the length of our half wavelength dipole will be 60 millimeters. So now I need to create the wire that will serve as my dipole antenna. I draw the arbitrary cylinder, give it a name, change material to conducting and realistic copper. Okay, change the color, something that looks like a copper, and change the dimensions. So my dipole will be oriented along the Z direction, and doesn't need to change this. I change the center position of the lower base to be minus length of the dipole, denoted by L dipole over 2, because my dipole will be centered in the center of my coordinate system. L dipole, as I said, is gonna be 60 millimeters. We need to change this unit type to length and millimeters by default, 60 millimeters. Okay, then height of my dipole is L deep. Apply. Okay, so this way we draw the first wire. Yes, probably I also need to change the radius because now it's too small. Let us do this R wire because this radius is gonna be the same for all elements of my antenna. And let's do something around maybe 1 millimeter. Okay, so standard radius of wire. So this is just the passive wire, passive piece of wire. I need to drive a current along this wire. So I need to insert the lumped element source that will play a role of the waveguide or a transmission line that drives this antenna. To do so, I need to cut away a piece in the center. with made of, so let us draw the auxiliary cylinder that we will cut away from the first one. So in order to draw this cylinder, let us again arrange this symmetrically along the z direction, and let us name this L, maybe P, L port over 2. Again, lengths in millimeters, and this gap in the center of this antenna, let's make it something around maybe 2 radiuses. Okay, so it's 2 millimeters. Okay, the height is LP, and the radius is R wire plus 1 millimeter. Okay, so it's a little bit thicker than the wire itself. Okay, double check that it is centered in the center of this wire. Run OK. And now I click on the dipole and the cylinder 1 and go to the Boolean operations and subtract. Double check that I subtract cylinder 1 from dipole and go OK. All right, so I've got this gap between two wires of copper. Then I need to insert my port. To do so, I draw the auxiliary rectangle in the X Z plane. Okay, I do right click in this mode, go to the grid plane and choose XZ plane. Okay, so this is a thin thin rectangle that is inserted in the gap of my antenna. Okay, now I can select this new element and then right click and then assign the excitation and lumped port. Okay, lumped port excitation corresponds to something like a generic waveguide with 50 ohm characteristic impedance of this waveguide. Okay, here I do next, and then I need to insert integration line. I click on this none, select new line, and draw a line between these 2 points on the auxiliary rectangle to create this red arrow. And next, renormalize almost to 50 ohm, which is the standard for the waveguides, like actual cable, and do OK, finish, and save the project. So now I can go to the project and see that my excitation appeared in this project manager. All right, so the antenna is made of copper, is driven by a source in the gap. What next I need to insert the boundary conditions. Okay, any problem must have some sort of boundary condition. In this radiation problem, my boundary condition gonna be radiation boundary condition. To do so, I draw a sphere around this antenna with the size something somewhat larger. It should be at least lambda over 4 from all elements of the antenna. Okay, so something like this would be totally fine. This sphere is made of vacuum, and I choose the sphere now and go to assign boundary radiation boundary condition. So my boundaries appeared here. Okay, so it's a radiation boundary condition. And in order to see my antenna, I just right-click sphere, go to view, and hide in all views, just to hide this sphere. All right, so now I can insert the analysis solution setup. I go to analysis, right-click, and then advanced. In this dialog form, I can set the operation frequency. So my problem is broadband. And I run and I simulate this antenna from 1 frequency to 5 gigahertz frequency. Let us change maximum number of passes to 10 to make this conversion to be better. And OK. As I run OK, I have this pop-up window where I can set the frequency sweep. For the frequency sweep for this problem, we change the sweep type to discrete, okay, to make these frequencies discrete, and I need the fields at every single frequency where I simulate my system. So I also enable these safe fields in all frequencies. I also change this distribution to linear step and make it going from 1 to 5 with a linear step of 0.15. I guess it's gonna be enough. and I do OK. All right, so analysis is set. Now I can go to the simulation, validate the simulation. All these check marks are green, which means that I can analyze the problem. So I run the simulation of this problem, which is gonna take a few minutes to be executed. All right, the simulation is over. On my computer, it took just maybe 2 minutes. So let us first plot the S11 parameter of this antenna. To do so, I go to the results, right-click, and create model solution data report and rectangular plot. So by default, it suggests me to plot S11 because this is the kind of most important parameter of any antenna. So this is the result. I see that my antenna works pretty well around the frequency of 2.2 gigahertz, which is very close to 2.5. You remember for the Hall wavelengths dipole, the resonant wavelengths or resonant frequency is supposed to be around 2.5. So 2.2 is very close to 2.5. I guess if we make the wire thinner, okay, and the gap smaller, we can shift this resonance closer to the theoretically predicted point. But anyway, so this 2.2 resonant frequency is good enough. My antenna has S11 minus 15 dB, which means that the vast majority of the energy that this antenna receives from the waveguide is radiated at this resonant frequency. So according to the Z parameter, we expect to have the imaginary part of the Z parameter. Actually, let me plot this first. So I do the same results, a rectangular plot, and the Z parameters. New report. New report. This is not what I need. I need a real and imaginary part of this Z parameter. So remember, Z parameter is the input impedance of my antenna. I'm interested in real part, which is which corresponds to the active resistance, right, of my input impedance of my antenna, and the imaginary part, which is reactance of my antenna, that corresponds to the or this describes the stored energy in the near field of my antenna. I do report, and I see that indeed at the frequency around 2.2 here, the imaginary part of input impedance goes through 0, right? So at this frequency, the antenna doesn't store energy in the near field, but radiates this energy in form of radiating waves. And the real part of input impedance is very close to 50 ohm. All right, so at this frequency, the antenna is very close to matched condition for antenna connected to the 50 ohm waveguide. All right, so this is first characteristic, S parameter, Z parameter. I also need to, I want to see how this antenna radiates at around this frequency. So in order to see this radiation pattern, I need to create the radiation setting, right? To do so, I right-click radiation, then insert far field setup and infinite sphere. Infinite sphere with theta going from 0 to pi, and phi going from minus pi to pi. I guess that's fine. I just changed the step size to make the calculation easier to 5. Okay. And as I did so, as I inserted this far field integration sphere, if I go to the results, right click, I can see now this option for creating far field report. Right, so I do 3D polar plot and directivity total, and I need to check the frequency. To do so, I go to setup sweep, and for the available frequencies, I allocate the frequency which is closest to 2.2, which is this one, and new report. All right, so this is the radiation pattern of my half wavelengths matched antenna at 2.2 gigahertz. So you see that this antenna doesn't radiate along its axis. This radiation is negligibly small here, and the antenna radiates to the sides in form of this figure, which reminds the donut or a donut, or this form is also known as a Rayleigh's butterfly. All right, actually, the section of this shape is called relays butterfly. All right. So this is the first part of my simulation, only just the dipole element. Now I need to simulate, I need to draw the Yagi-Uda antenna, and I will use this dipole active element as the active element of my Yagi-Uda antenna. So Yagi-Uda antenna consists of several parts. This is the active element. I'm gonna draw several pieces of wire like this, which will be passive. In the positive direction of X, I'm gonna put the passive elements called directors. They're gonna be a little bit shorter than somewhat like 5% shorter than the legs of this active element. Okay, these directors, according to their name, intend to form the near narrow radiation pattern because of constructive interference with radiation from this active dipole antenna. And it's going to be another element which is called a reflector, put on the back. It's going to be a little bit longer than this active element. And the purpose of this element is to destructively interfere and cancel down the radiation that goes to the back. Right, so let us start with the array of reflectors. I'm gonna put maybe 3 reflectors. To do so, solution exists. Do you want to? Yes. Before to do so, please save all the data for your report. All right, so I draw the cylinder in the center. Let us change this cylinder name to direct 1. Okay, and in the properties of this cylinder, I arrange this cylinder along Z direction. Change the center position to minus L director over 2. For the director over 2 unit type, again, the lengths in millimeters. So let us do something around maybe 5%. Okay, so it's typically 5% shorter. So 5% from 60 millimeters is going to be something around 57 millimeters. Local variable post-processing, change this to local variable. Okay. For the radius, we do RW. For the height, we do L deep. Apply. Okay. So I draw the element that is a little bit something wrong. L minus L deep, L deep, or L, oh, sorry, not deep, but L director. All right. Okay. So new element that is still made of air or vacuum. Let us change this material to enable as a part of model. Okay, and apply, and change this material to copper too. All right. So now this element is located in in the, by the way, let's change the name. Okay, that's director one. It's still located in the same spot as the first active element. We need to move this element to the right. So I select the director one and then do move in operations. First point in the center, and I shift this element in the right direction. So for the position of the director, let us do something around 18 millimeters. Okay, so I change this move from this arbitrary value to 18 millimeters from the active element. Okay, so this is my first director. Now I can select this director one, Control C and Control V to copy and paste this element. It gets the name director 2. And now I move this director 2 again in the right direction by another 18 millimeters. 18 millimeters supposed to be. Okay. Double check that this new element is the part of the model. Okay, so this one is checked. And I need the third element. Again, highlight, insert, move from the center by another 18 millimeters. Okay. We can also enable solve inside because this is a realistic metal. So this solving inside will correctly solve the characteristics like radiation efficiency of my antenna. Okay, so these are three directors. They are passive, but form a narrow radiation pattern in the forward direction because of the constructive interference. Let us create the last element, which is the reflector. Again, arbitrary cylinder. Change this name to reflector, material to copper, solve inside. Then in parameters, I do axis Z to arrange this along Z. For the center position, let us do -L reflector over 2. So for the reflector, it's gonna be something like 5% longer than the active element. Let us do another 3 millimeters. All right, so length millimeters and 3 millimeters means 63 millimeters for the length. Now the height is L reflector, radius RW, apply. Okay, and shift this element by at least lambda 15% of lambda. Okay, so it's gonna be Okay, it's gonna be lambda over 4, so 30 millimeters from the active element to the left. Move from the center to the left by 30 millimeters. 30 millimeters. All right. So this is our Yagi-Uda, simplest Yagi-Uda antenna. These all elements are made of copper. Now I double check that my new antenna fits within the integration sphere. It doesn't, so I need to change this radius to, let's say, 90. Okay, does it fit now? Yet, yes, it does. Let me show it and make transparent. Okay, so now this antenna fits nicely within this integrating, not integrating, but radiation boundary conditions. I save it. And so radiation boundary conditions are set. The analysis setup is set. Everything seems to be ready. The model, give me a second. This is what it says. Site solid with require a large mesh. Okay, so it suggests not to solve inside these elements. Okay, let's disable this for now. Okay, so we don't solve the fields inside the wires. Okay, now everything is fine, and I run analyze all. It's gonna take a few minutes. All right, my simulation is over. It took about 4 minutes on my side, and now I can check the S parameter, how it changed. So you see it changed. This resonant frequency shift towards to a little higher frequency. So now the resonance happens at the frequency 2.35 gigahertz. Going to the Z parameters, we can see why it happened. Okay, so that happened because this resonant frequency, the imaginary part of input impedance resonance, when this point goes through 0, when it changes sign from negative to positive, shift to the right. So if you remember from the lecture, this negative reactance corresponds to capacitive character of the element, and positive corresponds to inductive character of the element, right? So, and the fact that this point shifts to the right means that we have increased this capacitive character around this area because of the capacitive coupling between the elements, which is expected because now in the near field of this active element, we have these passive directors which work as the capacitive addition to the total input impedance. All right, so our operation frequency changed a little by 0.15 gigahertz. It's just a small variation. And the directivity pattern at the frequency 2.2, which is close to the optimum, is this one. So you see that now it is very directive radiation pattern. Thus, the total vast majority of the radiated energy is radiated to the forward direction, and the backward radiation is very significantly suppressed because of the presence of the reflector element. We also notice two side lobes which are very weak too. So this antenna can radiate as a very radiative element. That's it. Thank you very much. And for this laboratory work, please follow the tutorial and submit in the format of the in the traditional format that we use. Thank you for your attention.